Hi everyone, welcome to another video. Now, we in the previous video looked at solving some cubic equations. Now we are moving on to the idea of cubic functions. And all of these are in the form that we're going to be looking at the start here of y equals x cubed, or y equals some value in front of x cubed. But to start off with in this video, like we've done with all of the other functions, because these are really brand new, we're going to do a slow introductory video into sketching these ones here. And like with all of these, I have something with two variables, y and x. We can sketch this on the xy plane, and we're going to do so by starting off with a table of values. Okay, so let's go all the way from -3 up to +3. Okay, and what we're doing is we're going to substitute each of these into the x here. Now, substituting in -3 here, that gives me -3 all cubed. So in other words, this is just a shortcut for saying -3 times -3 times -3. That's what cubing a number means, timesing it 3 times by itself. So this gives me -3 times -3 gives me a positive number because of the double negative. That gives me 9, and multiplied by -3, that gives me -27. So we're going to write that in my table of values. That's going to be -27. And we're going to do this for all of these values here. For -2, I'm putting in -2 cubed, which is like saying -2 times -2 times -2. That gives me -8. -1, that's like saying -1 times -1 times -1. That gives me -1. 0 is going to just give me 0 because I have 3 zeros multiplying. 1 times 1 times 1 gives me 1. 2 times 2 times 2 gives me 8. 3 times 3 times 3 gives me 27. So we have drawn up this table of values, and you can see that for a change now, the numbers we're working with end up getting pretty big pretty quickly. Now if we compare this to something like a parabola, y equals x squared, because we're only squaring a number, timesing it by itself, the rate of increase is going to be a bit slower. Whereas here, since we're cubing a number, let's just think about this. This is like taking a number, timesing it by itself, then timesing it by itself again. We're going to get to these really big numbers really quickly. Now, if we draw this, obviously not to scale, because I have some massive numbers here. We want to investigate what this would look like. Okay, so starting at 0. Okay, now let's just write in some values of x. Now, when x is -3, y is all the way down at -27. So that's like, let's say, way down here. When x is -2, y is -8. So let's say that's about here. Obviously the scale is going to be a bit weird, so please forgive me, but we just want to get a feel for the general kind of shape. When x is -1, y is -1. That's about here. Let's make it a bit closer. When x is 0, y is 0. And then we get a similar thing happening up here. When x is 1, y is 1. When x is 2, y is 8. When x is 3, y is 27. That's like way up here. So, drawing these in, we get a bit of a like monster, massive looking graph. But we join up all of these dots and we get something looking like this. Okay, so let's zoom out a little bit, try to get the full picture of what's going on here. Let's just make some general observations about this. Well, first of all, it's kind of mirrored in a really nice way. Now, all of the negative numbers here produce negative results. All of the positive numbers here produce positive results. And 0 just gives us 0. So this thing kind of looks like it's mirrored but in opposite directions. This thing here and this thing down here. So we have the same y values, but they're just negative for the negative x values. So unlike something like the parabola, where we couldn't get negative values because squaring a negative number always gave us a positive, now we can move into the negative end of our xy plane. Now we'll just make an observation about one more thing here. We have this particular section here, which I've tried to shade in as obviously as possible. What happens at this point? Well, our function goes up and then it kind of stops momentarily. It kind of has something similar to a turning point for our parabolas, where they stopped momentarily and change direction. Whereas here, what happens is it stops momentarily at 0, the origin, at the coordinate 0, 0, and then it continues going up in the same direction. It doesn't actually change or turn. What we call this point here, it has a specific name. This thing here is what we call a point of inflection. This is a point that the graph momentarily becomes stationary, like it did when we looked at turning points in parabolas, but the reason it's different to a turning point is the graph doesn't turn, it doesn't go back down like a parabola would. It continues going up in the same direction. But this is what a general cubic will start to look like. And in the next couple of videos, we're going to look at some transformations for these particular cubics and look at how our regular one in the form of y equals x cubed can be changed and shifted around, stretched out in a bunch of different ways like we did with our other functions. Now, just checking as well, let's just double check that this is in fact a function. Now remember, our definition of a function was that one x value produces one y value. And we get this by doing what we said was a vertical line test. And we can see that no matter where we draw this vertical line, we have this one-to-one relationship where one x value is going to produce one y value. So this is a function. And we will explore this function a lot more in the next few videos. But thank you so much for joining me today. I'll see you next time.